Hey folks, we are about to finish up chapter 7. This last section is fairly short, and I think we'll get through this in one video. So this is section 3, and we're looking at gas mixtures and partial pressures. So we've already identified that when we talk about the gas laws, the identity of the gas does not come into play at all, right? It doesn't matter what gas we're talking about, the same laws and the same equations apply, right? So if we have a mixture of different gases, kinda doesn't really matter when it comes to like the total volume, total pressure, and things like that. Like if you have 1 mole of a gas and 1 mole of a different gas, you really just have 2 moles of gas, and that's kind of how we can think about it. So yeah, let's take a look at what this means and some of the implications of it. As I kind of was just saying, each gas in a mixture exerts a pressure independent of the other gases, right? The kinetic molecular theory tells us that gas particles do not interact with one another. There are no intermolecular forces of attraction between them. They're just flying through the container, straight lines, really fast, randomly. And so it doesn't really matter what gas it is, the pressure independent of any other gases there. So each gas behaves as if it alone occupied the total volume. So if we could look at the pressure of each gas in a mixture, we call that a partial pressure, right? Because it's a part of the total pressure. It's a contribution to the total pressure. The figure here shows oxygen and nitrogen, right? So let's say we have 1 atmosphere worth of oxygen gas, 2 atmospheres worth of nitrogen gas. And so if we were to combine them into something that had the same volume, same temperature, what we would end up with is just 3 atmospheres worth of gas, right? We add the numbers up. And if we think about the equation that we have here, that ultimately has all the relationships hidden inside of it, right? All of the individual gas laws inside the ideal gas law. Remember that we just are looking at the total number of moles in this case. And so we could look at like moles of gas 1 plus moles of gas 2, and we can look at the pressure of gas 1 and the pressure of gas 2. And I'm running out of room here, right? But we can basically substitute in like this. And here's really what we get. It's called Dalton's law of partial pressures. And we've been saying it all along, but to write it out, the total pressure is equal to the sum of all of the partial pressures up to however many there are. So it might only be 2, it might be 3, or up to n, however many there are. Okay, here's just another example. If we have a gas that occupies 200 kilopascals, which all you need to know is that kilopascal is a pressure unit. That's about it. If there's 200 kilopascals of, say, green, 500 kilopascals of red, and 400 kilopascals of blue, at the end, we just add them all up. As long as the volume has not also changed, then it's good, right? If the volume did change, it's fine. We can still just look at the total number of moles and see how things changed according to the ideal gas law. Okay. Here's a question. Practice exercise 735. A mixture of only nitrogen and oxygen has a total pressure of 3 atmospheres. If the partial pressure of oxygen is 0.63. What is the partial pressure of nitrogen? Okay, so we'll write out what we know and what we're looking for, and then we find the relationship between them. And we know that the partial pressures add up to make the total pressure. So if we're solving for P and 2, that would be the total pressure minus the pressure that oxygen gives. And so that would be 3 atmospheres minus 0.63 atmosphere. And the pressure that nitrogen exerts must be 2.37 atmospheres. All right. And here is that a little bit cleaner. So that's about it for partial pressures and mixtures. Now there's one more topic in this section, which is Henry's law. And this has to do with pressure and solubility. Solubility is dissolving in solution. It is specifically how much of a substance can be dissolved. All right, so I have here, we're going to walk through a way of thinking about this through a model, 3 containers, and each container will be filled with an equal amount of water, and then we will put some CO2 gas in this container, and there would be a lid here. By the way, you notice CO2? Looks like this. And if you recall, it's double bonds, right? CO double bond is a linear molecule. Anyway, there's our first condition. And then, let's say in the second container, we put twice as much CO2. So we double the pressure, right? Because moles is proportional to pressure, given constant volume and temperature. And in the third container, we double the pressure again and put now 4 times as much in the gas phase. So what happens to the solution? Here we see if you have particles above water, there's going to be equilibrium. As they hit the surface, they'll bounce off, and some will go in. Let's say we end up with 2 relative 2 particles dissolved. Notice when we double the pressure, we double the number of dissolved particles, and when we double the pressure again, we again double the number of dissolved particles. All right, and that's exactly what Henry's law relationship tells us. It says that the pressure of a gas is proportional to the concentration of the gas in the solution below it. So pressure is proportional to concentration, and we have now equal when we throw in there Henry's constant. Henry's constant is what that's called. And Henry's constant is substance dependent. Right? What I mean by substance dependent is each gas has a different Henry's constant. Right? So some will have at a given, let's say at a given concentration, it will have a given pressure. And some gases have higher Henry's constants, some have lower Henry constants, and you can look these kinds of things up in a table. But the key is that the concentration and the pressure are proportional. Another way to write this is actually to rearrange it and solve for concentration, right? So here you could say, I have a pressure of this certain gas. I know what it is. I know the Henry's constant. And what would the concentration be in a solution? And this is actually, the solution here could be blood, which would be a very common example for us. Like if you're giving an anesthetic as a gas, or even as not a gas, it would still have some vapor pressure. You can look at how it would move through the body. Would it be dissolved in the blood, or would it come out of the blood and diffuse through tissues directly, right? So when you write it this way, if you have a small Henry's constant, so Kh is small, then the concentration is higher, and the anesthetic would stay dissolved in the blood. If you have a anesthetic, however, with a high Henry's constant, then the concentration of that in the blood would be low, which means the gas would diffuse through the tissues directly, allowing it to reach the brain more rapidly, which would bring the onset of the anesthesia quicker, and it would also bring a quicker recovery. So that's it. All right, folks, that's what I have for section 7.3. So that wraps up chapter 7 for us. I'll see you next time.